So when we're talking about just the respiratory system, we're going to talk about pulmonary ventilation. So that's literally our ability to pull in air, the volumes that we're going to have that we're looking through different components of the breathing system, how we're going to diffuse that into the bloodstream, how we're then going to transport the gases we're looking for through our blood to where we need it, get the gas exchange again at our capillaries now in our muscles, and then what's effectively controlling the rate we're breathing. So the point of our respiratory system is to carry oxygen to the tissues that need it and remove carbon dioxide. That's it. We're going to do this by 4 basic types of processes. We have what's known as pulmonary ventilation. So that's our ability to literally breathe when we think about it. Pulmonary diffusion, which is where those gases are going to exchange in the capillaries of our lungs. Transport of that gas via our blood, thanks to being pumped around our body by our heart. And then the diffusion again inside of our capillaries to our muscles, to our liver, to our brain, to our heart, to whatever tissues need oxygenation, which turns out is most of it. So if we look on the right, what we're going to see there is the basics of spirometry, which is you have someone exhale into essentially a bell that happens to be surrounded by water. So we're only going to be capturing the amount of air that you're actually exhaling. And the amount of air that you're typically breathing in and out is what's known as tidal volume. Now, the total amount of air that you can breathe in with the biggest breath and exhale with the biggest breath, pushing out, crunching your abs, really trying to get the last little bit out, that's what's known as your vital capacity. Now, so from there, we have what's known as our inspiratory reserve, which is how much more you could breathe in if you really wanted to, and your expiratory reserve, how much more you could exhale if you wanted to from that tidal volume that we have at rest. Now, total lung capacity also incorporates dead space. So when you exhale completely, there's still air in your bronchi. There's still air in your trachea, in your larynx, in your mouth, in your nose. You cannot completely expel all of the air from your body, no matter how hard you try, which is a good thing. But that also leads itself to what's known as anatomical dead space, where we don't get gas exchange. So our lungs themselves are made up of a huge amount of pleural sacs, which are made up of a huge number of individual alveoli. And that's where we're actually going to get our gas exchange to occur. Now, our lungs themselves, the viscera, are effectively, we're going to have a layer on the outside, and then we have our actual inside of a rib cage. So whenever we talk about pulmonary and intrapulmonary pressure, that's what we're talking about, literally the connection between the two. Our lungs are just going to take the size and shape of a rib cage, but we're also pulling them down whenever we're inhaling deeply through our diaphragm, which hopefully is how we're doing most of our breathing at rest. Now, this means whenever we want to breathe in, we create a vacuum. We bring the diaphragm down, we expand the rib cage both out and upwards, and then from there, we're going to be creating a negative amount of pressure inside of our lung compared to outside, and that's going to pull air into our lungs. When we're exhaling, we're moving the lungs up, we're shrinking the rib cage down, and that is going to create a greater amount of pressure inside the body, pushing the air out. So we're using simple pressure gradients in order to allow us to breathe. Now, pulmonary ventilation, when it comes to that actual inspiration, guys, is look at the pressure differences. Now, your intrapleural pressure is that pressure between the lining, the exterior of your lung and the lining on the inside of your rib cage. We want this to always be lower than what's known as our intrapulmonic pressure, and that's the pressure inside the lungs. If that happens to ever be higher, the intrapleural pressure, that's called a collapsed lung, which happens usually due to severe accidents, and you don't want that to happen. Now, the active breathing in is an active process, and this is going to be the diaphragm pulling down. Our external intercostals are going to contract, moving the rib cage out and up, and we're even going to be using some accessory muscles on occasion when we're really pushing ourselves. Now, this is good because it's, once again, creating that bigger volume, creating that negative pressure, which in turn is going to be pulling air into the lungs. Now, as we've increased that lung volume, we have this lower pressure, and because nature abhors a vacuum, we are literally going to be pulling air from the atmosphere, notice that's the 760 millimeters mercury, into our lungs, so that we are going to now cause those levels to be normalized. Now, when we talk about taking bigger breaths, so the biggest one you can, you're going to be using the scalenes, your SCM, sternocleidomastoid. You're even going to be using your pec minor to help lift your rib cage and allow yourself to raise that rib cage even more so and allow you to breathe. How many of you guys saw, I guess over the summer, it kind of became a thing where a couple athletes posted links over to a reference that showed you actually recover faster from repeated sprints with your hands on your thighs as opposed to just trying to stand up. How many of you guys have seen that before? A couple of you guys, because usually it was a pro athlete that was talking about, I can't believe that, like, what was it? Every coach I've ever had should apologize to me for having me train that way. Or to say that, it doesn't help and you should put your hands over your head because it actually doesn't enhance your ability to recover faster. But one thing to keep in mind, when it comes to recovery, sometimes the point is actually to make things more severe. And what we're going to learn when it comes to your actual breathing, your breathing is not really that well tied to your oxygen saturation levels. It's more tied to your carbon dioxide levels. So when your carbon dioxide levels rise, that's when your body is going to tell you to breathe more. And so you can run yourself into situations with, so JJ Watt was one of those athletes that put that up there. Nice. So that's one of the things that's fascinating, especially as we're living in the wonderful COVID era of wearing masks. And you might be like, you feel like you're, I'm sure a couple of you guys have had that moment, like, I feel like I'm suffocating. Like it's so hard for me to breathe in this mask. Like I must be falling apart. But then if you were to actually look at your blood oxygen levels and otherwise, you're actually normal because effectively it's creating a greater stressor than you're used to, which in turn is causing your mind to freak out. But in reality, you're absolutely safe and it's nothing to be worried about. So when we exhale, usually it's just to relax. So, right now, guys, when I say breathe normally, then you start thinking about your breathing and you throw that all out the window, and that's okay. But I want you guys to just, you're just hanging out, you're just breathing, just being fine. And I want you guys to really think about, taking that really big breath, feel that rib cage expand, feel yourself maybe tense up a little bit in your neck, feel the ribs go up and out, trying to get in that biggest breath you can. Then really push everything out. Try to exhale as much air as you can, and you're going to feel those abs crunch in. You're going to feel those inner intercostals pulling your rib cage down. You may even feel your back starting to flex and otherwise, so that we're really trying to get all the air out possible. And we're doing this by creating a greater amount of pressure inside of our lungs to the external environment, which is going to, once again, drive that air out. Normally, when you guys just take it, if you go back to your normal breathing, you'll just feel like you breathe in and you just kind of relax and the air comes out. And that's just the nature of the beast of your diaphragm relaxing so it goes back up. It's just whenever we crunch it further by using our abdominals, we can get even more air out of the lungs. So the nice thing is, thanks to that breathing in and breathing out, we're actually creating pressure inside of our chest. So when we exhale, we're creating that positive pressure. So we're actually slowing down a little bit of that blood being returned to the heart, but when we're inhaling, we're creating a negative pressure, which in turn is allowing more blood to come back to the heart. And so thanks to this, we're actually going to naturally help with our heart functioning. And this also is going to give us one of the causes, along with changes in vagal tone, to what is known as your heart rate variability, which is if you're actually to look at your heart rate, like for an entire hour or over the course of an entire minute, yes, you do 60 beats per minute, but it's not a perfect metronome. It's not hitting on the exact same beat every single time. There's going to be points where it goes up a little bit faster and points where it goes down a little bit slower. And this is thanks to partially the respiratory pump, also thanks to vagal tone, which is part of a quality functioning of your parasympathetic nervous system, because it also receives pressure through that inhaling and exhaling cycling. And because of that, we can actually see how well recovered you are. So it's not just how low your resting heart rate is, but it's also how low is that heart rate variability, where a heart rate that has a greater amount of variability is typically, in trained athletes, so we always give the context, is a healthier heart or someone that's more well recovered because their body is not going through as much stress at rest. Any questions there? All right. So what's going on at rest? Well, it turns out our lungs are getting about 4 to 6 liters of air, depending on body size. Now, somebody like J.J. Watt might be closer to 7 because he is a very large human. And it might be less than 3 when you talk about very small individuals. And our cardiac output for our right ventricle and left ventricle, remember guys, is always going to be the same. The key is we've got much lower pressures when we're going through our pulmonary vasculature as opposed to whenever we're going through our our aortic and going through the systemic blood flow. So yes, we don't have to have as much muscle mass on our right ventricle as we do on our left ventricle. And because of that, we're not going to have as thick of walls, but we are going to have the same chamber size, okay? Because it turns out we're always going to be equally pumping the same volume of blood out of both ventricles. The key is left ventricle has to overcome that aortic pressure, which is much, much higher. Now, when we're talking about gases, guys, the first thing to understand is what's known as Dalton's law, which is the air that we're all breathing right now is just a little over 79% nitrogen. It's 20.93% oxygen on average. It's obviously going to be a little lower depending on where you're at, potentially a smidgen higher if you're hanging out in like a forest or something. It would definitely be lower if you happen to be around a bunch of car exhaust and other types of wonderful using a dead dinosaur to move around. And at this current point, it's about 0.03% carbon dioxide, but you know, it's rising. We'll see how much higher it goes, but you know, we might not live long enough that it matters. So fun. Now, that total air pressure, which when we think about air pressure, you often will hear like millimeters mercury or atmospheres, ATMs. So a normal atmospheric pressure in millimeters mercury is 760. Now, obviously, this air pressure can go up, and that's when we have what's known as a high pressure zone, which is typically where you have very few clouds. You are going to have perhaps a little bit more wind. Low pressure systems is typically where you're going to see more of like kind of storm fronts. And this is where some folks will talk about they can kind of feel in their joints effectively what the air pressure is like that day. So if it's a high pressure front going through, they're going to actually feel it better. When it's low pressure, because there's not as much literally tension through their systems, they're going to feel maybe not as well. Now, each of these gases is going to, when we add them together, equal the total air pressure. So if we have 760 millimeters mercury, we multiply that by 79.04, we get the partial pressure of nitrogen. We take that 760, multiply that by the percentage of oxygen in the air, and then we have the partial pressure of oxygen, and the same is to be said about carbon dioxide. Now, this is where people get themselves into trouble because they talk about how, oh, when you're up at altitude, there's not as much oxygen. There's actually the same percentage of oxygen. It's still 20.93%. The problem is the partial pressure of oxygen is far, far lower. So you're not able to, it's easier to breathe at elevation because you have less pressure to work against. However, you do not have as good of diffusion of oxygen into your body when you're at elevation. And we have pictured below, that's when we talk about those pleural sacs, where we have those individual alveoli, and where we're going to see that gas exchange occurring from the actual outside air to the capillaries. So the next big component is what's known as Henry's law, which is the gases in the air are going to dissolve into liquids in proportion to their partial pressure. So this means literally if we have a higher partial pressure of the gas, we're going to get more of it in the bloodstream. Now, it's going to, of course, depend on what type of fluid we're talking about, the general temperature, and the solubility given by that gas at whatever temperature we're at. So when we're trying to figure out how much we're going to get in exchange, always look at that partial pressure. Hence why when we go up in altitude, we're going to have an issue with oxygen gas exchange, or specifically getting in the body, because that partial pressure gets to become so low. Once again, it's that same 20.93% has not changed. Now, if it wasn't for these gradients, we wouldn't be able to take up as much air. And that's why some athletes will use hyperbaric oxygen as a means to help with recovery. So they're literally not just taking more oxygen, but they're also doing it in a higher pressure environment. And there's some interesting science showing that it might be useful. The problem is it's really hard to double blind. And then on the other side of it, you sometimes see athletes using just pure oxygen when they're recovering on the sideline, especially when they're playing at altitude, because the partial pressure of that gas is going to be lower the second you release it from the tank. However, you're going to, in theory, be able to saturate your bloodstream a little bit more with it because you're going to find that gradient to be a bit larger. Now, another thing to keep in mind is the inside of your lungs is incredibly humid. So notice when we're looking at this table below, guys, you can see how when you're moving from dry air, so obviously air with very low humidity, into alveolar air, where all of a sudden the partial pressure of water was at 0, and we've gone all the way up to 47, because it turns out we naturally do gas exchange in a very, well, my wife hates the term, but it's really what it is, a moist environment. And specifically, think about when it's cold outside and you can see your breath. That is literally the amount of moisture that you're losing with every single breath you take. If you were able to actually, measure out exactly your total amount of water lost through breathing each day, you would typically see this could be as high as over a liter each day of literal water loss you have literally through the act of breathing. Now, we're going to be getting that gas exchange in the alveoli. So we take that initial partial pressure of oxygen in our plain air. Then we get it to the alveoli. Remember, it drops down considerably thanks to the wonders of the water pressure that we have. Now, the pulmonary arterial pressure, meaning coming back from the veins of the body, left the right ventricle, coming through the pulmonary artery, is very low. It's about 40 millimeters mercury. So that gradient is going to be showing us how much we're able to top it off. So the gradient is 65, typically gets up to about 100 millimeters mercury when that blood is going through the capillaries and there's oxygen obviously readily available. Now then that oxygenated blood is going to return to the left atria, left ventricle, be pumped throughout the body, go to the capillaries where it will then in turn be picked up and utilized accordingly. Now, how much gas we're able to exchange is also related to what's known as Fick's law, which is the amount of diffusion we're going to have is proportional, to the total amount of surface area we have available and our total amount of pressure gradient. So if we have more surface area and we're going to have a greater amount of partial pressure, we're going to be able to pick up more oxygen and give off more carbon dioxide. Now, the other component to keep in mind here is it's also going to be inversely related to the total thickness of that tissue that it happens to be being exchanged across. What this means, and this is actually part of the nature of how our lungs work, is not only do we have a huge number of alveoli, which massively increases our total surface area, and we've obviously have these given gradients that we can't really modify too much outside of using, specific mixed gases and otherwise to breathe through, but we're in turn going to go ahead and have very, very thin thicknesses. That's where you saw those endothelium cells that are effectively mashed about as flat as they could be. So we're talking about it, the gas is really moving only a couple microns. So yes, very, very small distances. So each gas is going to have its own diffusion rate. Carbon dioxide actually diffuses relatively easily compared to oxygen. And whereas we're going to need to do more in order to get that oxygen to exchange, if you guys think back to the previous graph. Now, the total amount of oxygen exchange we have is going to be based upon, obviously, the volume that we're going to be diffusing per minute, per millimeter of oxygen. And we can then calculate it when we look at the total average amount of oxygen, both from whenever we happen to be getting it into first the pulmonary artery, and then whenever it's returning and going out to the extremities. And we're going to find that this total amount of gradient is usually about 21 mils of oxygen per minute per millimeter mercury when it comes to that gradient. Now, this is in turn going to give us a total amount of, in this one, 231, when we're looking at an 11 millimeter gradient from one side to the other. However, we're going to find that it's going to become even greater at maximal exercise because we're going to be extracting far more oxygen from the blood that's returning into pulmonary circulation. And since we've removed more oxygen, we're gonna have a bigger gradient. And this can literally go up to 3 times what we find at resting, which is going to allow us obviously to load up a lot more oxygen to then release at the tissues that happen to be needing it. Now, another big key that limits our total oxygen diffusion at rest is literally due to what's known as incomplete lung perfusion, meaning at rest, thanks to the wonders of gravity, your upper third of your lung is actually not getting that good of blood flow. Your bottom third is getting full blood flow and your middle third is doing okay. And that's because literally our heart isn't pumping with that much intensity. It's not creating enough pressure to fully utilize the blood, essentially to push the blood through the upper third of the lungs. So we're not going to be getting all of the potential gas exchange. Now, once we start exercising, we're going to get way better oxygen diffusion because we're literally perfusing the entire lungs with blood flow at a high enough rate that it allows for all of those capillaries around all of those alveoli to be utilized optimally. Now, once we get that oxygen in the blood, we're going to find that we can usually carry about 20 milliliters of oxygen per 100 milliliters of blood. Most of this oxygen is going to be bound up into hemoglobin for allowing it to be transported. And remember, you're going to have millions of individual hemoglobin inside of your red blood cells, to which you have potentially billions of those floating through you as we speak. And so when we put an oxygen in, bind it up inside of the heme group of a hemoglobin, we have what's known as oxyhemoglobin. When we've removed that oxygen, we now have what's known as deoxyhemoglobin, and about a little less than 2% of oxygen is actually just going to be free floating inside of your bloodstream, but most of it is going to be bound up to hemoglobin. Now, hemoglobin is really interesting because it has what's known as a saturation curve, which means depending on how much oxygen is around it is going to influence how much it's effectively going to release oxygen to the blood around it. So what does that mean? It means if you look at our value in the, or you look at the graph on the right, when we happen to have really high amounts of oxygen levels inside of our blood, hemoglobin doesn't let go of oxygen. It's like we don't need to release it because there's so much more available. But as we are going to decrease that partial pressure of oxygen, meaning we're starting to get around our capillaries of exercising muscles, we're going to start to unload a little bit faster. But notice, guys, our veins at rest, yeah, we're to that 40 millimeter mercury. So we still have nearly over 75% oxygen saturation of hemoglobin. When we start exercising, however, we're going to see that veins at rest, partial pressure of oxygen, we're going to get all the way down to a partial pressure of oxygen potentially at 0 around the really heavy exercising muscles that the capillaries are having to go by. So we're literally going to get nearly a full unloading of hemoglobin. So the nice thing here effectively is when oxygen levels are high, it's not releasing that oxygen from hemoglobin so that it's not being wasted. But as soon as levels start to drop and they drop really low, it's going to release it rapidly. So that way those tissues are going to have a lot more oxygen available to them. Now, what's also interesting is the environment around the cell, not just oxygen, but the pH and the temperature are going to influence the dissociation of oxygen from hemoglobin. Now, if you guys are looking at the graphs, and we're looking at the one on the left, we see as the pH decreases, notice how hemoglobin is releasing more oxygen. And then when we look at temperature, when the temperature rises, we are going to be releasing more oxygen. So my question to you guys is, where in the body naturally are we going to find a lower pH and a higher temperature? So we're going to be more aggressively releasing oxygen. Where in the body are we going to find this naturally occurring? A lower pH and a higher temperature. No, not necessarily. Well, the stomach does have a lower pH. Not bad there, Zach. But we're hopefully not bleeding into our stomach, so that actually becomes a thing. When you think about the exterior, the pH effect is not there. Abdominal area, not quite sure how I follow on that one, Jake. Trendon, when we say our muscles, specifically when?
During exercise.
Bingo. So notice the way that we naturally are going to release oxygen from hemoglobin, it actually is going to release it faster when the muscles are warm and when they're having to utilize more anaerobic glycolysis. So we're dropping the pH level, which in turn is going to free up oxygen even faster. So we can hopefully not have to use anaerobic energy systems as much, but either way, we're going to make more oxygen available to those cells. So that's a really cool natural effect of hemoglobin is your lungs, the pH is naturally going to be a little higher and your temperature is going to be a little bit lower. But then when you really start working out, you're going to see no, it's okay, Jake, that's okay. But your organs are not really that warm. Hopefully they're not. If you find your liver running that hot, you should probably calm down on the drinking. Otherwise, our body tends to be at about that, 98.6 plus or minus, because there is some variance between people. But when you start exercising, it's very normal to have a body temperature of over 100 degrees Fahrenheit when you really start working. So, good. So, we naturally have a limit to how much oxygen we can carry around the body. It tends to be obviously related to how much hemoglobin we have. So most of our hemoglobin tends to be about that 98 to 99% saturated at rest. Now we're going to have lower saturation with exercise. Specifically, when I say saturation, literally how much we can fill up, because since the blood is being pumped through the heart at a faster rate, we're not able to completely top off the oxygen levels in each of those red blood cells' hemoglobin because they don't have as much time to linger. So why we care about our hemoglobin content is obviously that's going to influence how much oxygen we're going to be able to carry. So individuals that are anemic are naturally going to have a lower amount of red blood cells, which means they're going to have a lower amount of hemoglobin. And if they have a lower amount of hemoglobin, in turn, they're going to have a lower oxygen carrying capacity, which means they're going to have lower aerobic performance. And how many of you guys have either had anemia or you know of an athlete that became anemic? And you're more likely of all groups to find it actually with female athletes, because women are on what I heard referred to at a conference as a monthly phlebotomy schedule, aka, since women, once they're post-menarche, pre-menopause, they're having a period where they're going to naturally lose a little bit of blood each month, and a little bit might be a misnomer depending on obviously individual variances in flow. And on top of that, if you happen to be an athlete doing a large volume of aerobic style work, aka a female cross-country runner, you're going to run yourself into issues of going through and having a lot more hemoglobin overturn. And then finally, if on top of that you happen to be an athlete that eats a diet that naturally doesn't have a lot of iron available, aka you're not eating a lot of red meat, or if you are a vegetarian, you're not exactly timing things optimally. So the key is to make sure that we're going to, if we have an athlete that's not performing like you'd think aerobically, just to check to make sure that they're not becoming anemic. So it's 2:15, guys. We're going to talk about carbon dioxide transport in the blood whenever we meet up on Wednesday. Do you guys have any questions for me? Lab this week is going to be the body composition lab. The goal is for you guys to come in throughout the week and do a Tanita. I'm going to try to put some quick videos up on how to run the bod pod. And myself and Dr. Fuchs are the only people that can run the DEXA scanner, so that becomes a limiting factor. And then we'll also try to go through the actual locations for the skin fold calipers, so you guys can have that and try to do it on your own, or just, pair up. We're not going to have you guys go through and do, multiple measurements on multiple people, but when you guys do the scans, gloves are going to be in the lab. You have your face shields and your masks you guys should have. You're going to be wearing all that equipment, and just be safe. But we'll talk more about that on Wednesday. Questions, comments, or concerns? All right, guys. Well, as always, thanks for coming, and have yourself a great day, guys. Bye-bye.